Good morning, guys. All right, we'll continue this chapter. That means one more thing about second order partial derivative, even for that matter, third order and so on. And one of the things that we are going to work on as example that missing element is the second degree Taylor polynomial. Second degree. Hold on, let me spotlight. Second degree. Okay, as you know, before we learn, we have discussed about linearization. About the ization of functions at the point AB. If you remember, this is L of xy, which is actually approximating f of xy, is defined by f of AB plus the partial derivative of f at AB with respect to x and x minus a plus the partial derivative with respect to y at the same point AB and y minus b. This was linearization. And this graph, actually, when you zoom in the graph of the function, it will be nearly matching the tangent line. And now, well, what about quadratic? If f has continuous second order partial derivative, at that point AB, then the quadratic approximation, that means the second degree Taylor, it will be f of AB and plus this linear f partial derivative at AB of x minus a plus the partial derivative at AB y minus b, and then plus 1/2 of the second partial derivative with respect to x at AB, and this is x minus a is going to be squared, and we have 1/2 of twice of the partial derivative because we have two partial derivatives when you expand that, but 1/2 will be cancelled, so the partial derivative with respect to xy, and it is x minus a y minus b plus, I ran out of space, 1/2 the partial derivative with respect to yy at AB and y minus b squared. And this is the called quadratic approximation or second degree Taylor. So what do we do? Just like what we have done before, here the involved elements are the function value at the point AB, the first partial derivative at point AB with respect to x and with respect to y, and then the second partial derivative at the same point AB. That means the mixed partial derivative, the twice partial derivative with respect to x and with respect to y. After you calculate, you plug it into the formula, and you will get your result. Okay, let's do example. Find the first and second. Degrees. Tyler. Polynomials L and Q for f of xy defined by e raised to negative x squared minus y squared at the point 0, 0. Go ahead and start it, and we'll do it together. Well, as I said, we have to actually evaluate at 0, 0, 6 elements. That means f of xy and the partial derivative with respect to of xy and the partial derivative with respect to y, xy, the mixed, the second partial derivative with respect to xx, and the second partial derivative with respect to xy or yx, and the partial derivative with respect to yy. We are going to find all this. Okay, finding this, well, f of xy, it is really e raised to negative x squared minus y squared. Then from here, f of 0, 0 is going to be 1, because when you put 0 here and 0 here, e the power of 0 is 1. And now let us find the partial derivative with respect to x. This is going to be negative 2x e raised to negative x squared minus y squared. And when we evaluate that at 0, 0, what happened? X is 0, therefore, regardless of this one, this is going to be 0. And the partial derivative with respect to y is going to be, by the similar argument, negative 2y e raised to negative x squared minus y squared. And at the point 0, 0, this is also 0. Okay. Is it clear so far what I am doing?
I think there was a little bit of an error in the formula you gave above, but the process so far here.
What is the formula?
It should be plus the mixed partial derivative.
Yeah, this one is plus, yes.
And if that's fxy at a comma b times x minus a,
yeah, a
times
b,
y minus b.
X minus a and y minus b. Okay, thank you. Yeah, I was rushing and so on. That's it. All right, thank you for that. Actually, and then now let us find the partial derivative with respect to xx. And when we are finding the partial derivative with respect to xx, well, we differentiate this one. So we apply product rule. So I have negative 2 e raised to negative x squared minus y squared, and then plus or minus 2x, and then the derivative of 2x is negative 2x, so plus 2x e raised to x squared y squared and minus. All right, so when I really combine this one, because this is plus, so 4x squared minus 2 e raised to negative x squared minus y squared. And when I evaluate that at 0, 0, so I have here 0, but negative 2, and e the power of 0 is 1, so this is equal to negative 2. When we are finding the partial derivative with respect to x and then y, so this is a really coefficient. So this is going to be negative 2y. You have 4x y e raised to negative x squared minus y squared. And this will give me at so because both x and y are 0, so this term is going to be 0. And finally, the partial derivative with respect to y. Well, just like we did here, it is similar argument, but it will be 4y squared minus 2 is the power of negative x squared minus y squared. And this is going to be negative 2. Here also negative 2. I don't know why I put that. Okay, we get all this. And then now what we need to do is carrying out all this element, we will really plug it into our function. So the first Taylor is going to be L of xy is equal to f of 0, 0, because the point we are given is 0, 0, plus the partial derivative with respect to x at 0, 0, and x minus 0, plus the partial derivative with respect to y at 0, 0, and y minus 0. And this will give us, well, this one is already 1, and the partial derivative with respect to x is 0, and x minus 0, plus that is also 0. So generally what we get is 1. So at the origin, this function can be really have a value of 1, which is really constant. In that neighborhood, whatever value you put, the value is going to be near 0. Yeah, whether you are putting x equals 0.09 or 1.001, still the answer is going to be for y 1. All right, the quadratic approximation. Yeah, this is really a little bit of too much, but plus 1/2 the partial derivative with respect to xx at 0, 0, and x minus 0 squared, plus the mixed partial derivative at 0, 0, which I screwed up when I wrote it, and plus 1/2 the partial derivative with respect to y at the point 0, 0. And that is y minus 0 also squared. So as you see, this term is already done for us. We don't have to write it. So that is 1. And then now what I'm going to do is plus 1/2 of the partial derivative with respect to x is negative 2 and x minus 0 squared plus the mixed partial derivative 0, x minus 0, y minus 0 plus 1/2 and the negative 2 is for that, and that is y minus 0 squared. So this will give me 1, and this is actually negative 1, and you have negative x squared. And this, the whole thing is 0, and this is by the same argument, negative y squared. So the quadratic approximation is this. So this one is by far better approximate than the linear one, and this is what you need to do. Okay, I'll give you one very simple example, and then we will really call it off. Is it clear what we have done, guys? All right. By the way, have you seen the warm-up announcement? Who requested me to postpone the chapter 14 homework? One of you. Yes? Yesterday. Yeah. Okay. Well, actually, I postponed it for next week because I don't want to focus on this because you have the test. So you can do it next Saturday. Okay? So focus on the test. And the test also, I posted on announcement. All right. So now, here it is. Find the first and the second.
Professor, a quick question.
Yes, sir.
How long will the exam or the test be?
How long?
Yeah, how much time do we get?
Well, actually, I'm selecting problems and so on, and I'm going to take the average time. Was the quiz time sufficient enough?
Okay, I see.
Yes. So I will really adjust to that. You have at least 15 to 17 problems, and then accordingly, because some problems will take a little bit longer, some are. So it will show me actually the average time, and I'll do adjustment. Okay. And actually, if you ask me on Friday, I will tell you exactly what time, how long will be the test. Okay.
Okay. Thank you.
Okay. This time very simple at the point 10. Okay, so what I'm asking you here is, I want to find the Taylor first degree L and the Taylor second degree Q, and of this function at the point 10. Then once you have done, actually linearization is really to approximate value. So why not you compare the function value, because it is easy to calculate the function value, then the linear approximation, and then the quadratic approximation at 0.9 and 0.1. Tomorrow we are going to start multiple integrals. We'll work with double integral, and actually some of you might have really recent memory, some of you might forget it. And integral, as you know, it takes a lot. And I know that we didn't touch triple integral. We will really, I am assuming that it is not review. I'll go through that in depth. And then if we work with triple integral, actually, not only in Cartesian coordinates, but also in cylindrical and spherical coordinates, we'll work on that. Then we will work after chapter 16, vector field, streamline, and so on. And then all these skills that we spent, all these are going to be instrumental, and using them, we move that forward. If you remember in your physics class, engineering class, and so on, what do they do? Well, they will work with the theory and solve problems, and the mathematics aspect. They said, oh, as you know it from this, that's it, because they are assuming that you learn it. And that is what we are going to do when we are working the vector analysis from chapter 17 all the way up to 20. Okay, the function is x e raised to y, and at 1, 0, this is 1, and this is a power of 0 is also 1. 1 times 1 is 1. And the derivative with respect to x is going to be simply e raised to y. And at the point f 1, 0, well, e the power of 0 is also 1. And the partial derivative with respect to y is going to be, well, x is constant, the derivative of e raised to y is e raised to y. So coefficient times the derivative. And at the point 0, 1, this is going to be x is 1, is the power of 0 is also 1. And now let us find the partial derivative with respect to x. That means we are differentiating e raised to y with respect to x. And that is 0. And obviously, f at 1, 0 is going to be 0. And the partial derivative with respect to x, then we are going to differentiate it with respect to y. So I am going to differentiate with respect to y, e raised to y. That is simply e raised to y. And at the point 1, 0, where the value of y is 0, is the power of 0 is 1. And the partial derivative with respect to y, that means at xy, I'm differentiating with respect to y, the x times e raised to y. Well, x is constant, that's the coefficient. The derivative of e raised to y is e raised to y. So this function at 1, 0, obviously will be 1. Then let us find the linearization. It will be f of 1, 0 plus the partial derivative with respect to x at 1, 0, x minus 1 plus the partial derivative with respect to y at 0.10 times y minus 0. So plugging all this, 1 plus this is 1 and x minus 1 plus 1 times y minus 0, and this will lead us to 1 plus x minus 1 plus y, which is simply xy. So the linearization is xy. Okay, well, after that, what we need to do is let us find the second or the quadratic approximation. And yeah, it is a matter of writing. As long as you did it, you'll be fine. Patiently. I mean, if you do it patiently, you'll be fine. You saw me. When I am rushing also, I make error. Plus 1/2 the partial with respect to xx at 0.10, and that is x minus 1 squared plus the partial derivative with respect to xy at 1, 0 and x minus 1 and y minus 0 plus 1/2 the partial derivative with respect to y 1, 0 and y minus 0 squared. Okay. Wow, it's a matter of writing. As you see, this the first term is simplified. You don't have to put it. That is simply x plus y. And then now what I'm going to do is plus 1/2. And that's the partial derivative is 0. And x minus 1 squared plus 1 times the partial derivative x minus 1, because we have here 1, and y minus 0, plus 1/2 times 1 and y minus 0 squared. Okay, so I have x plus y, and this term is 0, and this is going to be xy minus y. And plus 1/2 y squared. So y by y will be cancelled, and this will be x plus xy plus 1/2 y squared is the quadratic approximation. So now what we are going to do is we have to evaluate f of 1, 0. That means 1 times is a power of I'm sorry, f of 0.9 and 0.1. And that means the x value is 0.9 and the y value is 0.1, and that will give us approximately 0.9947. That is the f value. And the L 0.09, 0.1, that is simply it is x plus y, so 0.9 plus 0.1, which is equal to 1. Well, that is okay, good enough. And now the quadratic approximation at 0.9, 0.1. Well, the approximation is x, that is 0.9, plus x times y, 0.9 multiplied by 0.1 plus 1/2 0.1 squared. And if you really use your calculator, and you'll get 0.995. Okay, while the exact value is this one, 0.9947. The quadratic approximation is close to the reality, and the linear approximation is not that far, because this point is really. So this is how actually calculators and computers are doing or giving us numerical value. It is programmed, and the precision is going to be determined by what kind of actually polynomial it is approximated. All computers, calculators and so on, when they are doing actually numerical operation, they only perform the 4 arithmetic operations: addition, subtraction, multiplication, and division. And if you see here, all these are polynomials, and even if it is exponent, it is really repeated addition. That is what is really, multiplication, what is really happening. Okay, so those of you who are going to be programmer, actually one of the tasks that we are going to be generating this kind of number. All right, so the next section that we are going to talk about is differentiability. And this is really very simple concept. Remember, a function is differentiable for single variable function if it is continuous and smooth. That means no cut, no jump, no hole, no sharp corner, or vertical tangent line. That's it. But for functions of two variables, differentiability is a little bit different. And in single variable also, if a function is differentiable, we can find actually a tangent line at that point, and the function value in that neighborhood of point of tangency, and the linearization value approximately will be there. So when you zoom in into that curve, the curve is becoming a straight line. And likewise, also, if a function is differentiable in multivariable, well, there is a tangent plane approximation. So at the point of near this point of tangency, the surface is going to be flattened, similar to this, the tangent plane. So we can use linearization for that matter, if it's differentiable. So a differentiability for function of two variables. A function f of xy is differentiable at the point AB if there is a linearization L of xy, which is f of AB, and this one m, I wrote it actually, it is a partial derivative with respect to x at that point AB, and x minus a, and n is the partial derivative with respect to y at the point AB, y minus b. If you remember, we write linearization at the very beginning when we learn the rate of change in the direction of x with respect to y, and the rate of change of z in the direction of y is this n. So we are bringing all together. So what will happen? If since L is approximating, that means f of xy is equal to, instead of being approximated, L of xy plus that error. Then the error is going to be the difference between the function value and the linearization. If h is equal to x minus a and y equals k equals y minus b, then relative error is going to be e of a plus h, comma, b plus k, divided by, we are normalizing the h and k squared, their sum. And that will be satisfying because the error, if linearization is taking place, as h and k are approaching to 0, the limit has to approach to 0. If the function is differentiable on a region R, if it is differentiable at each point in R, the function L of x is called the local linearization of f of x be near that. So look, this is the green, as I'm assuming this is a tangent plane, and this is the surface with the blue. And then the error is going to be in this area, this one. That means between the surface and the tangent plane. And for what value? Well, if AB is located here, and A plus H and B plus K will be located here, the distance is going to be that. You remember when we normalize, we divide by the distance. All right, let's do one example, and I'm going to move very quickly because we are running out of time. So show that if f is a differentiable function with local linearization L of xy at the point AB, this form, then m is the partial derivative with respect to x at AB, and n is the partial derivative with respect to y at AB. Look, this linearization is, in other words, it is the same. So when we are evaluating limits, let us assume L of xy is approaching to 0, the relative error, the E of xy. Suppose h is positive and k is equal to 0, then what do we do? 0 equals e raised to a plus h, b plus k over h minus k. This is the formula which I will do. Then now, because k is 0, a plus h, comma, b over h you have. Well, this actually error is the same as the difference between the function value f of a plus h minus b and the linearization a plus h, comma, b over h. Well, if this is the case, then now what we need to do is the linearization is going to be what? F of AB, M minus M. You remember it is H plus some 0 that is going to be, and the K value is 0. We have this term. So factoring out actually H, reducing by H, this will be M. But when you look at this one and this one, this is really the partial derivative with respect to X, which is and minus M. And you can make similar argument like that. So it is linearization. Well, when is actually the function is not differentiable? In order a function to be differentiable at a point 1, the partial derivative with respect to x and y has to exist, and then those partial derivatives in the neighborhood of AB, within the disk that contains AB, has to be continuous. Otherwise, it is not really differentiable. So if you look at, for example, this, it is the upper half of a cone. And at the point 0, 0, if you try to make linearization, no way this is going to be flattened. It will be sharp pinpointed. Therefore, we are not going to have tangent plane. Well, that is the argument we can make by observing. But observation cannot be really a proof. So let us check if it is really by computing the partial derivative. Well, if we differentiate the partial derivative at this point, f of h0 minus f of 0 by actually h is approaching to 0. And this will be what? Square root of h squared plus 0, because that is what we have, and over h. And then now this is along the x direction we are really finding the partial derivative. So this is going to be what? Square root of h squared is absolute value of h. Absolute value of h divided by h is always plus or minus 1, because absolute value of h is h when h is greater than 0, and absolute value of h equals negative h when h is less than 0. Therefore, when we are evaluating limit, we have to evaluate limit from both sides, left and right side. So left side limit is not really matching with the right side of limit. Limit does not exist. If limit does not exist, well, partial derivative does not exist either. Therefore, f is not differentiable. And there is another example actually where both f and partial derivative with respect to x and with respect to y exist, but because it is not continuous in that neighborhood, then the function is not differentiable. Please look at the example 3 in your textbook, and that will do it for today. Thank you for your attention. Well, as I said, tomorrow we'll start chapter 16. I hope this helped. I will see you tomorrow. Take care, guys.
Thanks.